Awesome. Hello and welcome everybody to RevDev number 1. And the first presentation is called Scooby Where Art Thou? If you can connect it with some cartoons that maybe you have been watching as a kid, because I have, then good for you. If you haven't, then you haven't really lost that much, but it was fun when I was young. Anyway, my name is Andrzej Grzesik. If you cannot say it quickly, you can call me Axe. This is how everybody in the company refers to me because nobody can spell it except for people from Poland. This is why my email is ags@revolut.com. Also, if you want the slides, email me and I'll be very happy to share them with you. Via email, of course. You can, of course, tweet at me or you can visit my dead blog, so don't visit it really. Use Twitter. And a couple facts about me. I run a conference. I'm a Java champion, Java on Rockstar. I'm involved more or less actively in some other meetups. And originally from Kraków in Poland, the city where we are. And I live in London for the past almost 10 years. So far it's been nice. A couple facts about Revolut. You've heard everything about Revolut that you needed to know from Wojtek, so I'm not going to repeat that part except for this one. Of course, we're hiring. So if you want to work here, it's very easy. Just say so, and we'll try to put you through the recruitment process, which should be fun and quick and efficient and nice to both the candidates and the interviewers. And then you can join. Of course, as an employee of Revolut, I do not represent the views of the company. All of the mistakes and all of the opinions are my own. And apologies if I misconvince you in any other strange direction. If you have any questions about the talk, this is the way to interact. Raise your hands, or raise your hands with glasses if you actually enjoyed that part of the talk, and ask. If you have any questions about Revolut, let's do them outside of the talk, in the break, or after. And I like dry jokes, and I like motivational slides, well, those kinds of them. So here is one, and here is another. By the way, it's useful to ask questions today because we have 2 licenses for IntelliJ IDEA or anything by JetBrains to give to people, so people who ask decent quality questions can get them. Good. We'll start with this fundamental problem in computing. Where do bytes live? Have any one of you seen a single byte in a computer? Well, the answer obviously is no, but somebody can say that bytes usually are in RAM or in memory. That would be a good intuition, but then we will say, okay, let's go deeper. And the question will become, how do you read exactly 1 byte? Who can tell me how to read exactly 1 byte from memory? 1, 2, 3, so okay, nobody. Good. The problem is you can't. Or you can, but it's not that easy. There is an intermediary level of magic. So what happens, depending on the CPU architecture, I'm assuming x86 or AMD x64, so something reasonably modern and popular, you're not going to read a single byte cell from memory because such thing does not exist. What you are going to read is a cache line from memory, so a chunk of memory, and then using magic of masking, so binary instructions, which are going to give you exactly the byte that you were after, you're going to read the value of the byte that you were after. Of course, if you want multiple bytes, that becomes, well, a very simple thing. Which leads us to a very important conclusion that byte is an illusion. But it is, and it's not, and it's all at the same time. It's like dualizm korpuskularno-falowy, but worse. I do not know what it is in English, sorry. Why am I talking about this? And why am I showing you data specs for old Intel CPUs? There is a reason to it. What are we looking at first? We're looking at 2 randomly chosen or semi-randomly chosen CPUs by Intel. One of them is Q313 release date, and one of them is Q314. The left one has less cores, so 10 normal cores, 20 hyper-threaded. The right one has 14 cores, 28 hyper-threaded. So far, so good, no major changes. There is one important difference. The important difference is in memory bandwidth. The left one has 59.7 gigabytes per second. The rightmost has 68 gigabytes per second. So the newer, the bigger one has more. Everybody's happy. So far, progress is as expected. The caveat is, if you do it by core, then the left one is 6 gigabytes per second per core, and the right one is 4.8 gigabytes per second per core, which means it sounds like a decrease, and that's suspicious. But it's not suspicious, this is exactly what's happening. And then if we compare that previous CPU with a very modern, very recent Intel 11900, so last gen, top of the line consumer CPU, you will see that that one had 8 cores and 16 threads, which means, yeah, quite a lot. But its memory bandwidth is only 50 gigabytes per second. So 50 gigabytes is less than 68, obviously, but it's actually more per core. And what does it tell us? Well, it tells us one very specific thing, that there is Moore's law, about which most of you have heard, and those of you who haven't can read about on Wikipedia. I'm not going to remind anybody of it because that's not important here. There is a thing called processor memory performance gap, or memory gap, or you can call it capybara if you prefer to. The problem is CPUs increase in the amount of instructions and the amount of computing that they can do, but at the same time, memory does not increase in its speed as quickly as CPUs. And this is a problem. And this is a very big problem if you consider that modern, very big CPUs from, for example, AMD can give you 64 physical cores or 128 hyper-threaded, and memory bandwidth behind, powering those cores is a bit behind on the performance. And you could ask now a question, okay, what's industry doing with that? Well, the answer is, well, there's a couple actually. One of them is we're getting DDR5s. Who here has a DDR5 base machine? Nobody yet. That will change. Over time, that will change. DDR5 is a song of the future, or it's a very current thing. Why are we getting DDR5s? Because they can give you higher transfer speeds. So more transfers back and from memory, which means more bandwidth. This is a way to work around the gap. Not completely circumvented, but diminishing factor. Another expected effect is we are getting more channels. You've heard of dual channel long time ago if you were reading about hardware. Now you can get quad channel. Now modern server CPUs will give you hexa channel. They will also very often give you octa channel, which means you need 8 almost identical memory sticks inserted, and CPU will through magic and very well executed orchestration read memory from all of them at the same time, or almost at the same time, and it's a bit more complicated, but you get the idea. This is a way to work around the lack of expected increase of speed through which one memory stick is being interacted with at. And also, one unexpected effect is Intel stopped publishing memory bandwidth on their CPU spec sheets. If you check most recent Xeons, there was nothing, or at least I saw nothing when I checked it yesterday. And now, let's go back to garbage collection. But before that, this. Garbage collection, as we all know it and love it and use it, is a process in which, in an automated fashion, memory is being examined, and if it's not being used anymore, or if there are objects which are not being used or accessed anymore, they are being removed without us, programmers, doing anything. Which means the role of the GC, so that we all start from the very same playing field, is to run next to your application code in parallel, in cycles, in phases, however you want to have it, and eliminate garbage. So if we didn't have a GC, we, as programmers, could all go in and type free everything, delete everything, whatever memory allocation library you're using. And GC will sometimes invoke itself, and sometimes it is going to run, and it's going to go as expected. And this is the contract that we have with the garbage collector. It's going to do what we would have to do manually for us, automatically. So the fact that it runs, it's okay. So what about tuning? Do we need to tune it? I'm not going to answer this question just yet. Also, I know Christian is going to talk about that much more. But one consideration here is, because there is this thing that everybody says GC in Java or in any other managed environment is slow. Well, I will pose a hypothesis. Is it really? Is it the garbage collector, the automated process that actually tries to evacuate and eliminate all of the useless objects that is being slow, or is it what we, the programmers, are hoping, cursing, making the computer do, making garbage collector do much work? And also, when somebody says slow, what exactly do you mean by slow? Is it low throughput? Is it high latency? Is it pausing for a long? Because there are different kinds of slow. And if you have to move, the fact that you have a Ferrari is, well, it's beautiful and it's very pleasant, but it's still useless. So, on this slide, if you can see it, you can see it. If you cannot, it reads Java lang out of memory error, Java heap space. Who here has seen such an error? Around half of the room is not shy enough to raise their hands. The others will, or they are trying to eradicate this from their memory. When do we get this error? We get it when Java or any other managed environment, but I'm basing this talk on the JVM, obviously, is unable to allocate something. Well, in here, in the stacks arrays, actually, I was trying to make a very large array because life is too short to make small arrays sometimes. And when do we get that? When the settings of heap do not allow this. What are the default settings of the heap is the question that we have to think about for a bit. There is a thing called JVM ergonomics. And JVM ergonomics is a concept introduced long time ago around JDK, I think 5 or 6. Many years, which govern what are the reasonable defaults for the garbage collector and heap settings for, well, when running on a specific system. And they say that if you have a computer that is considered server grade, your heap space is going to be from between 1/64 to 1/4 of your total memory dedicated to heap. And so you're going to use a specific garbage collector, and then you're going to use the server compiler. And what makes a server-grade machine? Well, if you have 2 or more physical processors, who here has a smartwatch? Whose smartwatch has less than 2 cores? QED. 2 or more gigabytes of physical memory. I think even if you buy a picture frame right now, it's going to have 2 gigs, at least. Which means everything now, because of that, by Java is considered server grade, which is accurate because it is very powerful. Somebody could say, hey, but we are now using JDK 17 if you've been following some of my other talks about Java upgrades, or maybe JDK 11 plus if you're slightly behind. What's changed? Well, what changed is that the default garbage collector is going to be G1 rather than, for example, CMS, but the sizes for memory are going to be exactly the same. So by default, if you do not set anything, Java is going to use up to 1/4 of your operating system reported memory for its heap. If you put a single application in Java only onto a system, you're probably wasting around 70%, maybe 65%, because operating system obviously needs some buffers. One thing to consider. And then, if you run your Java in Docker, I really hope that nobody does, but still, I keep meeting people who run very old Java in Docker, as in very old, as in Java 1.8 before build 191. Java is not going to completely correctly figure out how much memory is available to it. If you run something decent and modern, it is, so that is not a problem. Why is that a factor? Because if you put, for example, only 2 CPUs or 1 CPU available to your Docker container, and then you run something that cannot figure it out, it's going to consider that the host machine is the server, which it is, but it's going to expect Java to have much more compute and memory available to it, while it hasn't, because obviously you have, through the magic of C groups and Docker, limited that, which will affect the default heap size, which will affect the default number of CPUs, which will affect then in turn thread pools and sizes of other things like that. But that's a side note. How do we set memory? Who here thinks that in order to correctly limit garbage collector adjusting the memory while the JVM is running, setting XMS and XMX is enough? Well, it is a leading question, so obviously you need another flag. Why is that? Because garbage collectors, apart from having a start and a maximum heap space, they also have something called adaptive size policy. And if you don't disable it explicitly, you are going to, and it's perfectly within spec and expected behavior of such a garbage collector to actually modify the heap space that's being used by the JVM, even though you have set start and max to a specific value. Which means if you do that, then please use all 3 flags. And then we can talk about yet another concept. The concept of throughput. because we talked about what makes an application slow. Now let's look at application being slow through a particular lens. So throughput for the needs of the stock is going to be defined as the time that the application spent running your application code, as opposed to running, for example, the garbage collector code. How can we read it? Well, you can, for example, see the garbage collection CPU time, and as your intuition guides you correctly, garbage collector CPU time should be low, and that means that time available for your application to do the important, the interesting, the reward-bringing stuff is going to be high. And so we can see it maybe on a graph. What are the GC-induced up pause times of a specific application that I run that I'm not going to share the code with, but it doesn't really matter what's being run here. Can you, by looking at this picture, say whether it's good or it's bad? And to people who cannot see the bottom of the slide, the blue lines, which are right here in the bottom, are young generation cycles, and the red ones, which you can see plenty of, are full GCs. And the full GCs do form a line around 3-second mark, and this line is pretty consistent from at least 23 o'clock up until, I think, 1:20, when I got bored running this. Is it okay or is it not? It doesn't look good. That's a very correct observation. Let's convert this picture to maybe this thing, or maybe instead of looking at this slide, we're going to look at this other classic. The other classic says, out of memory error, GC overhead limit exceeded. Who of you has seen it? Nobody? Somebody must have. Maybe you've evacuated the memories. Do you know when is this exception? Well, where is this error actually triggered? It is triggered when the amount of time the JVM has spent running garbage collector code, as opposed to JVM was able to run your application code, has exceeded a specific percentage. And by default, this percentage is set to 98, which means in any 100 units of time, if 98 of those were dedicated to GC, then JVM will say, I'm not dealing with this anymore, table flip, and going home. So if you have a process that was running, for example, for 100 minutes, after 98, the JVM will give up only. If you think that this is quite inefficient or slow, I'm going to agree with you completely, because it is extremely slow and it's extremely late. But this is because JVM is very optimistic about your application being able to run given the conditions that you were trying to get it to. So we have this error. We have those graphs that we can figure them out. Do you know how to get the data for generating such graphs? Some of you must know, but for the benefit of others, the answer is enable GC logging in production. This is one of the possible answers. There are more, but we'll talk about them slightly later. So how do you enable GC logging in production? Who here still uses JDK 8? Java 8? Nobody? Some hands, of course. It's okay. If somebody's using 6, it's also socially acceptable. We're a very tolerant community. We accept people who use Java, even if it's version 1.1. And it's a peculiar choice, but hey, we're still okay with that. JDK 8, you would have something like that: Java minus verbose GC minus xlog GC, The exact flags don't really matter, but this is the kind of invocation or incantation that you're going to see there. And this is going to give you an output that the garbage collector is going to log to. You can even use timestamps, magic. If you want to have a slightly better set of data being printed out, maybe you want to include those flags, but well, it really depends what you want to do. If you're in a more modern JDK, like 9 and onwards, you are affected by something called unified JVM logging, JEP 158. And I have to quote it by number because I've heard that anytime you quote any JEP by number, you appear smarter. So of course I have to. The bottom line is, the invocation changed, and instead of doing the previous set of flags, you now say x log gc, and you say which things you want how much detail about, and what is the file, and because I find you, as the audience, as very intelligent, I am not going to ask you to memorize this, even if some of you are students and expect this on an exam. No, it's not going to happen. The links are available, and I'm happy to share the slides, really. Nobody should learn this by heart. So there is a number of options that is available. There is also documentation about how to convert old-style GC log instructions into the new ones. And then there is another caveat. If you're using those logs, if you're running a JDK that doesn't have async GC log writing, then if your GC log output is going to be considered part of the time that garbage collector was running for. Which means if you're, for example, writing your garbage collector files into a spinning drive, which has a lot of other random access competing for it, it is going to be extremely, extremely, extremely slow. And we can all only hope that I know it through looking at the internet, not any particular painful experiences speak for it. So we know this. But there are also other Java options available to us. And this is a very important one. The very important one, if you are going to do any sort of investigation with performance, with garbage collector, with anything else, what's happening, trying to tell what's happening in the JVM is called -xx plus print flags final, which is going to do exactly as the name suggests. It's going to list all the flags and their values in a specific JVM invocation. Why is that important? The answer is on the slide, because some flags will trigger changes to some other flags. And also, some flags will conflict or override some other flags as well, which means if you have, for example, a number of flags that you've amassed over the life of your system, let's say over the past 5 years, and maybe there is a very active manager who really wanted to add his own special favorite flag of the day to every single build, and I've met such people, then this is going to at least tell you that it's not you going insane, the flags as set might be incompatible, or this is the final flag that the JVM actually accepted and runs with, rather than what is in the running script. Some caveats when talking about flags, they change between releases, and changing one might affect the others. So again, well, print out all. And if you need a point of reference, there are two amazing sources. One of them is the JDK source code. It's a lot of C, quite some Java, have fun. But there is one more practical source called code.Techniques, a page that looks like this, or looked like this yesterday. Today with Cloudflare having problems, I have no idea what it looks like. It lists all of the flags for a lot of JVMs and a lot of JVM versions and minor releases as well. And you can search through it, and you can read what they affect and how are they, when are they applicable to which CPU, to which operating system, and so on and so on. Awesome reference place. Don't learn it, use this website. There is no point to learn it by heart. If you're a student, there is definitely no need to learn it. If you're a university teacher, if you try to examine anybody based on this, I'll find Liam Neeson to do you know what to you. And so, JDK 8 and others have something like Java, -xx plus heap dump on out of memory error. And you give it a path for the heap dump, and then we're good. If we have a memory problem, we're going to just load this file into a profiler, we're going to analyze it, we're going to be able to tell what the problem with performance is. Yes or no? Obviously, this is a leading question again, so obviously the answer is not really that simple, but having spoken of flags, I forgot to mention this one. If you're running a multi-physical processor system, or if you're running a processor that basically is affected by NUMA, which as time goes on is going to be more and more processors because they are no longer single silicon dice anymore. Some JDKs used to, because this refers to the older ones more often than the new ones, didn't detect those facts correctly, so you had to explicitly set use NUMA. If you don't know what NUMA is, this is JVM accounting for that you might have two physical CPUs and two physically allocated memory banks associated with those CPUs so that it benefits from it. But we talked about, sorry, we talked about GC logs. It's finally a question to ask, what can they tell us? This is what they look like. It's an example. They might look differently to you, obviously. This is what they look, this is also what they might look like. What do you do with this amount of text? Option number 1, write a lot of regex. It is a possibility, but my recommendation is don't do it. Use a GC log analyzer. Some of the GC log analyzers that I'm going to mention are GC Easy, which is on a website available for free. You don't have to pay anybody. You have no idea what they do with your GC logs. But at the same time, GC logs are really, in most cases, not that secret. So if you upload them to a random website on the internet, even the infosec of your company might be okay with that. There's also HPJ meter. There used to be an awesome thing that I really like, and that this particular computer still has a running version of something called jClarity Sensum. And there is an amazing toolkit by Apple called GCGC, and there is a lot of good things made available by Microsoft who acquired jClarity called GC Toolkit. And then if you use a specific JVM, you might get other additional specific toolkit from them. I'm going to be showing you pictures based on jClarity Sensum because they make good pictures. The information obtained in them is obtainable in any of the tools that I've listed and many others. So it's nothing secret or special that they do. They just organized the data in something that's useful. So what can we get out of a GC log? We can usually look at different kinds of information. One of them, we can see what is the heap utilization. So basically, how much of the heap are we using? What are the sizes of specific memory pools? Then we can see what are the pause times, what is the application throughput. You now know what throughput is, how much of the application runtime was dedicated to the GC versus the application. Were there any explicit, maybe system GC invocations? And then you can see allocation rates out of this, how much heap is being recovered, what were the save pointing statistics, and so on and so on and so on. First of all, we're going to look at a summary. A summary is going to tell us that in the duration of 93,000 seconds or slightly above, we have accumulated or we have allocated 26 terabytes of data. Is it a lot? Is it not a lot? Depends on the point of view. But you now know that there is a limit to allocating because you cannot, by laws of physics, allocate more than your CPU's memory bandwidth is. Because there is no physical way, even if you exercise prayers, that you're going to put more data into your memory than the memory is going to accept. So this is why allocation rate is a very useful thing to observe if your application is being very slow and you allocate a ton, a metric or a non-metric ton, then it is going to lead to a problem. This application that I generated here actually had a very stable allocation rate, as you can see, over 24 hours, no pun intended. It was allocating in a stable way. We don't see anything jerky here, which means it's stable and it's okay. How can you test it quickly? There is one way. If you have a hypothesis that your application should be okay to allocate maybe 200 megabytes per second or per hour or per whatever, and then you want the application to be able to run for X amount of time, you can use something called no GCGC. It sounds counterintuitive, but in those precise cases, this is exactly what might help you. And it's actually built into the GK. It's called Epsilon. It is a garbage collector that does nothing. You use it through these flags, and again, you don't have to memorize them. The slides are available if you want them. And yeah, what's going to happen after you use it? Your application is going to run a specific amount of time, and at some point, it is going to run out of memory because this is a garbage collector that does nothing, after all. And then you might want to get a heap dump, and then you can actually get a heap dump, and you're going to be starting to analyze a heap dump. How would you analyze a heap dump? Second? Somebody said JHeap. Any others? There are a lot of tools. Yes, that is true. I cannot disagree. Somebody said Eclipse Memory Analyzer. Yeah, that's a very good choice. There is more. You can use JProfiler, you can use YourKit, you can use JFluid, which is the thing within NetBeans or Visual VM. You can use some others. JDK Mission Control as well. Somebody said IDEA. Probably I actually didn't try it, but maybe it can. Now, if you are going to do that, you are going to see some caveats. First of all, a heap dump from a 16 gigabyte heap is going to be larger than 16 gigabytes. That's caveat number one, which means you will have to adjust heap space for your memory analyzers accordingly, because it might run out of memory. So if you find the fact that you run out of memory trying to analyze an out of memory because of out of memory, then yes, it is ironic. Some tools will also fail when trying to parse and analyze some heaps. This sadly is normal, and it happens. And this is why I mention a lot of them. And this is why when I have to deal with something like that, I use a lot of them. The first one that does it wins. But sometimes I will, for example, try to open the same heap dump in two tools at the same time and see which one loads it faster. Because things happen. And when you're dealing with a 48 gigabyte heap, things happen and unexpected things happen as well. And loading a large heap dump can take a while. Again, 40 gigs can take 20 minutes, can take an hour. Now imagine some servers can have 2 terabytes of RAM, and if you give a lot of that to the JVM, it is going to take a while, and you will have a need for a production-like machine in order to analyze it. Which brings us to screenshots. This is a screenshot from actually Eclipse Memory Analyzer. Again, all of the tools can do the same. It doesn't matter which one you're going to use. They are all equally good. Usually you're going to see some common themes like histogram, which is going to give you how many instances of a specific class or how much space do specific classes take. What are the dominator trees, so the biggest objects, and what makes the biggest object the biggest object. What are the top consumers, so the most expensive objects, and you can group them and slice and dice as you expect. Duplicate classes, finding duplicates, maybe duplicate strings. And this is a picture from YourKit. As I said, exactly same analysis is available there as well. If you're going to use JProfiler, you're going to see something very similar here as well. But then, when you have a particularly big heap to analyze, there is a very useful tool called JHeapo that can take a heap dump and process it and put it into a graph. And it's going to put this graph into a format that is native to Neo4j, which makes it awesome. And it means that you can analyze your things interactively like you would with any other Neo4j graph. But there is a caveat. This tool is now dead as in Parrot, as in the past 2 years. It hasn't seen a single commit. So if the heap dump that you're going to use is not correctly parsed by it, well, you can fix it. Good thing is, it mostly works because the garbage collector, well, the heap dump formats haven't changed massively in the past at least a few years. And it's useful. But now we get a quiz time. And in the quiz time, we have a question. The question is, or what are we looking even at? We're looking at a heap dump that associates a huge number of instances in a Java-lang thread. And it sees 24 million strings, which occupy 1.3 gigabyte of memory, which makes all of the things associated with this thread very, very heavy. And question to you, my dear audience, is how would you analyze this situation? Or maybe you can guess what the culprit was in here. And while you think, I'm going to drink. Somebody's saying concatenating strings in a loop. It's a good guess because you see a lot of strings. So your intuition of something to do with strings would be correct. But garbage collector would be able to eliminate the strings that are no longer referenced, which means it's not that. But I appreciate the attempt. Storing them in a list. No, those strings are not stored anywhere because they are referenced by this thread only. There is no other object that actually collects those strings. This is just this. Using constructor to create strings. Yeah, but if they would be short-lived, then they would not occupy this amount of memory. I see a hand there. Go ahead. Maybe there is a hash map. No, it's like the list. You would see the list instance or the hash map instance being listed in here, and it would actually be owning the instances of the string. I'm going to give you a hint. The heap dump, the hint looks like this. It's including some JNI. For the people who can see it, thanks to the great light, good for them. For the rest of you, I'm going to try to read it. So what we're doing here is we're allocating a few new string UTFs, and we're going to call a static methods within the JVM. Pretty normally looking C code or C++ code. Do you see an error here? Somebody said JNI pinning. What do you mean? Somebody said that memory is not being released after it's being allocated in JNI. Yes, good. You've actually solved it. The problem was that if you're creating new strings on using JNI, you have to delete the references because otherwise you still have a reference, even though it's evacuated through C++. Well, glory to JNI. And do you need an IntelliJ license? Good, if you have to, then you'll have to. Why am I showing you this? The reason is very simple. A profiler alone is not enough. Garbage collector logs alone are not enough. You need to think, and you will have to, if you want to solve garbage collector puzzles, you will have to sadly read the sources as well, because you might find flowers like this. And yes, which means we can move on a bit to byte buffers. You probably use Netty. Do you use Netty? Yes, of course you use Netty. Netty is awesome. Netty is amazing. Thank you, Netty, for being Netty. Netty uses byte buffers. And not only Netty uses byte buffers, but byte buffers are a thing. What are byte buffers? Chunks of memory allocated off heap. So they are not directly garbage collected. And they are going to occupy memory. So they are going to count against RSS of your JVM process, but they are not going to be affected by XMX or anything like that. Which means if you want to figure out what's happening with them, well, you will have to be a bit more creative. If you want to limit the size, you have a flag, and then you have a default that they will use. And then if you want to see allocations, my recommended way to go forward with that is to replace default malloc with gmalloc. And this is going to tell you how much everybody is allocating with memory buffers. And it is going to produce a log through which you analyze, and that's that. Primitives are another very popular culprit when it comes to memory consumption. Specifically, if you do something like this, and wink, wink, it doesn't have to be long, it can be integer, it can be double, it can be float, it doesn't have to be array list, it can be heap, hash map, or anything else. The bottom line is, if you use collections of capital case primitive types, or basically primitive type wrappers, you are going to waste quite a lot of memory. And you're going to waste some performance as well. Now, why do you waste memory? Because if you have a lowercase int in Java, it's a primitive. You get exactly this cell in memory. It stores a value of the int. There is nothing else. On the other hand, if you have an integer object, it is an object which has this int internally, which means also there is the indirection that your CPU will have to traverse anytime it interacts with such an object. And then if you put them in into a collection, you have an array. of objects, of the wrappers, that then point to different ints everywhere. And that puts pressure on your GC, and that puts pressure on your application. Now, here we're looking at a random application. As in random, it doesn't matter what it does. But what happens here is we can see allocation rate, cumulative allocation of a specific sample app. And we can see that, for example, at minute 31, there was almost zero allocation. Then at minute 33, we've had 1.9 thousand megabytes of allocation, so almost 2 gigs. I think it doesn't allocate too crazily, but you can see some pressure. What happens if we replaced, or what happened when I replaced the array list of long to a long array list? This is what was present in the GC log. So what we can see is the amount of memory that needed to be allocated and the amount of memory that needed to be default processed by the garbage collector has seriously increased. And if you're done playing with your Apple Watches, we're going to have another look at another diagram, runtime comparison of a long-running, long-intensive program. So another sample application in which the only difference between those two algorithms was instead of using array list of long, I replaced that with a long array list. And I thought it might be an interesting experiment because it might bear some fruit. And what you can see, the algorithm is obviously not going to pass any end of studies exam because obviously it looks quadratic because, hey, it's actually a 2D simulation, which is quadratic in size here. So that expectation is fulfilled. But what we can see is that it can bring us 200 seconds back from 769 down to 513 observed runtime. For everything. The only thing that I changed in this was replace specialized collections where generic collections of capital type wrappers were being used. So if your applications are using a lot of hash maps or array lists or sets or anything like that of longs, doubles, floats, integers, and you're in Java, then you probably want to consider doing that. How do you make a decision that you should do it? Well, you run a benchmark, you run the application with one, you replace it, and you compare the runtime, and then if the runtime is more satisfying than the previous, then obviously you've made a good choice. Which specialized collections should you use? I'm not going to point you at any specific one, so you're not going to get which one is the best kind of answer from me. I'm going just to say that using specialized collections is a thing. If you're using Eclipse collections they are called Eclipse collections, they are a very good choice. If you're using FastUtil, it's a very good choice. If you use something else, it's also a very good choice. But please, please, please also run your own benchmarks. Don't replace them just because you think this is the right thing, the best thing to do, because you don't know if you haven't benchmarked. Allocation profiling. Allocations keeps being a theme that I mentioned. And if I want to see what is creating allocations, what is allocating, then I can use, for example, JFluid, so NetBeans or Visual VM Profiler, which means I click onto Profiler, I click onto Memory, and there should be some more arrows happening here, but for some reason they are not materializing. But there should be a thing that asks me, do I want to record allocations? I would, of course, answer yes, and then you wait. And then this is going to be much slower than you expect because the profiler will have to do a lot of work in order to record which objects are allocated where. But this is going to be able to tell you in which pieces of your code you're creating the most garbage. Not to create the most garbage that garbage collector will have to consume, but create most objects that have to be stored on the heap, so where you allocate the most, which means if you want to focus on your allocation rates and focus on your allocations and optimize this area of the application, this is how you find entry points or pieces of interest. And having spoken of allocation profiling, there is a thing that's intrinsically connected, which is escape analysis. Which of the newly allocated objects escape? And it's a very popular research area, so there is a ton of papers. A long time ago, when I checked how many papers mention escape analysis at Java, I got 26,000 results. Now it's going to be much more. How would you do it in Java? You use a couple of flags, and you use a tool called JITwatch. JITwatch is a tool that looks like this. It was going to interpret the source or open the source, and it's going to say that there is an allocation happening, and that object, that maybe new wrapper, that whatever we have in there is going to escape. So it's going to be promoted to the next higher tier of memory within your GC, which means this is going to put pressure on your GC. What is the bottom line here? Sadly, there is no silver bullet. That's probably obvious, probably expected, but this needs to be said. You will need to run your own benchmarks, ideally in an isolated environment, and it should be reasonably similar to what you run your applications in production with, because if, for example, you run your JDK on a Linux that runs x86 or AMD 64, and you develop on a MacBook, it's a very useful and a very nice typewriter, but this is not the best tool to do production profiling or guessing about performance of the target environment. And also, you should be distrustful. You should design experiments that are going to prove whether what you're trying to judge or misjudge is actually having an effect, because sometimes you might find something that looks almost too good to be true, and then you might find that it actually is. As in, too good to be true, it's not true. And with that, I would almost be out of my talking, and as a short reminder, obviously, if you want the slides, ags@revdev.com, and if you want to work with me, the careers page, and so on and so on. What other tools should you use? Mission control. And I keep hearing that mission control you need a license for, and this is not true. Since Java Mission Control, version 7, it is completely open source. You can use it in production. You don't need to pay Oracle license. You don't need to pay anybody else a license. And then some of you could say, hey, but why do you tell us about Java Mission Control? There are profilers. Well, there is one magical thing that Java Mission Control can do to a living JVM, or one magical thing that a living running in production JVM can do that Java Mission Control can then interpret, and that's called a flight recording. So you can connect to an application running in production, ask it to perform a flight recording of everything that's happening to its GC. And this is a screenshot from Java Mission Control. And you can ask it which kind of events do you want to record. And then it is going to perform this recording. And you can do it in production. You can enable this recording for maybe 2 minutes on a specific one instance of your applications in prod. It's not going to freeze. It's not going to die down completely. There is usually a small performance penalty, but it's small, as in single-digit performance, single-digit percentage points rather than anything crazy. And then you can analyze it. And you can analyze it on a screen like this. I'm not going to try to even explain and show all of the things that JDK Mission Control can do when it comes to analyzing GC specs, but because you can safely, and I will repeat, safely connect and analyze an application in prod and record the data about an application running in prod, it is useful. If you take one thing out of this talk, use Java Mission Control against an application in prod is what you can do, if you really need it. Obviously, ideally, don't get to a place in which you need it, but if you need it, then you need it. Another question that you could ask, since I didn't say anything about garbage collector tuning, when would I tune? Well, one aspect of that is, first of all, if your goal requires tuning. There is a secret about the applications that we run in Revolut, is that most of those applications don't have any garbage collector settings whatsoever. This is because we are in a happy land of Java 11 or later for all of those applications, and we run with G1, and this G1 for the kind of services that we do is good enough. We don't have GC problems. It is because we don't run any crazily extremely latency latency services, as in we're operating single millis per request kind of latency budget, which is pretty generous to modern Java, to modern CPUs. If you have anything more stringent, your mileage might vary. But if you're doing microservices that power a mobile or a web interface, you probably are in a similar boat, which means if you're using modern Java, you actually don't need to tune in most cases. If you're, on the other hand, running your own Cassandra, then you might need to. Or if you're in a team that actually develops their own Cassandra, or develops something like Cassandra, because such tools exist as well, then you'll need to do it. I didn't even talk about tuning because it is a subject of its own, and it's a broad one, and it's a tough one. But instead of tuning, what you can do as software developers that have access to the services that you're dealing with is what you can usually much more easily do is change the code, which gives you superpowers, because usually if you just decrease the amount of objects allocated, this is going to say, this is going to result in garbage collector having to do less work, which is going to result in your applications running faster, in most cases. If you need to tune, that's what I can recommend. I would disagree with Amazon still about the date in which this book was published. But maybe those people have foreseen things before things. And then if you need to analyze native memory usage and what's happening there is an awesome talk by Andrzej available on this, at this link. Other noteworthy things, async profiler, which happens to be available in IntelliJ Ultimate near you if you want an IntelliJ Ultimate license. For some, I know a lot of people for whom this feature was enough of a justification to get the IntelliJ Ultimate. And as a reminder, we've allocated one license. We still have another for the good attendees of this meetup to allocate to. And then if you need to troubleshoot native memory in Java, you, on the surface, have a built-in thing. It's a flag called Java -XX plus native memory tracking. But there is a caveat. The caveat is it tracks only JVM mallocs, and it has a measurable performance penalty, which means it's basically unusable unless you are analyzing what the JVM does under the hood. And I think it's a good time for me to say thank you, ask for your questions, give you some time to refresh on the food and on the drinks, and give the floor to Christian. So your questions, good people. Yes.
I wonder, do you have experience with... Sure. Hello.
Okay.
So do you have any experience with Graal VM, and how this knowledge is applying to that? Is like behaving same way or not necessarily?
You're talking Graal native image, or are you talking Graal compiler?
JVM. If you run JVM or Graal VM.
If you're using Graal VM, then okay. The thing with Graal is Graal enables you to do a native image, which means JVM and things will be compiled to moral equivalent of a C compilation product, which means you're going to get native code, and it's going to get a different performance profile than a than a normal Java runtime being used. So if we're talking about that, then that's one question and one answer. And there is another answer, which is about Graal VM specifically. If you use Graal VM as your JVM in a normal way. If that's what you mean, then everything I said here applies to Graal, because Graal is it is an alternative JVM, but it still runs similar garbage collector algorithms under the hood. I'm going to say similar, not the same, because I haven't looked at Graal in the past month at least, so I do not remember what is in there. But if you look at it under the hood, it is based on OpenJDK after all. It has a lot of specialization, a lot of great tricks around the compiler area. But to see the details, I would have to give it a look. Bottom line is, if you allocate less, it's going to run faster because GC will have to do less work. But if you have anything more specific, let's talk outside of this talk. Anybody else? There is a hand from behind. A microphone is coming towards you. And the dear people from the internet, if you're asking any questions, I have no idea about it.
Hello.
Hello.
You will say that for Android Studio, you know, with the tools that this tool have, this is a better way or can give us more information?
I don't think I fully capture your question.
Sorry. For example, imagine that I'm develop an app, okay, in a native Android. So means that I have Java, right? So
some people would disagree whether you do, but yeah.
Yes. But means that you know, I'm using the garbage collector there, you know. So you will say that Android Studio provide enough tools in order to me have the information that I need related with the memory.
I don't know. I don't use Android Studio because I don't do Android apps on a daily basis. So we can have a look together and we can see whether it's. I would guess so, but it's only me guessing because I don't do Android.
Okay, okay.
But the principles will be the same because Android as a VM will have a garbage collector and the principles will remain. And I think the tools will be very similar. And if there is nobody else, then I'm going to have to say thank you very much for listening to me. Enjoy your drinks. May the force be with you.